Okay, work energy theorem is what we're going to start with today. So if I can actually get this thing to work. Ready? Oh, there it goes. Okay. Work energy theorem. And what the work energy theorem is it's a relationship between kinetic energy, I can't spell, kinetic energy and work. And there are two basic ways to interpret the work energy theorem, and we'll go through each interpretation as we go through this. And I really want to try to emphasize the work energy theorem because most people forget that it's a thing to do. So like in AP Physics, most people be like, "Oh, hey, I think about work." They're like, "Oh yeah, work equals force times distance." And I'm like, "Yeah, and then they're like, it equals MAD, so mass times acceleration times distance, which is the same thing." So it didn't really help you. It's like, and okay, but this is another way. Yeah, so the kinetic energy, so if we write that out, capital K is equal to 1/2 mv squared, and that is an energy measurement, and that energy measurement is in joules. Okay, so just like work is measured out in joules too. And here's how this works, no pun intended, because it's the work energy theorem. The amount of work done is going to equal the change in kinetic energy. So writing it out in kind of like a pseudo equation, the work done is equal to the change in kinetic energy in KE. To write it down as a equation, nice and compact, what it's going to come out to be is it's going to be that the net work on an object, so W net, so if you add them all together, is going to equal the KF, the final kinetic energy, minus the initial kinetic energy, or another way to write it is just delta K. So if you want to be lazy and you don't want to write out Kf minus Ki, you can write delta K and it means the exact same thing. That just means that it's the change in kinetic energy. And whenever it comes down to it, things. Go ahead. I don't care. Like it doesn't matter to me. Like what is my preference on how you write it? I honestly don't care. If you write delta K, I understand exactly what you're talking about. If you write out Kf minus Ki, I know exactly what you're talking about. If you don't like slopes, or if you don't necessarily like algebra in of itself, or if physics problems actually hurt you a little bit, my recommendation is to do Kf minus Ki, because that kind of reminds you Kf is my final kinetic energy and Ki is my initial kinetic energy. So it kind of gives you a little bit of a setup to the problem. So if you're just starting out, I would recommend Kf minus Ki. If you look at it and you're like, okay, I'm okay with this, delta K is the way that you would actually do it. Okay. It does happen sometimes. It do be like that. Okay, okay, okay. Come on, come on. There are two interpretations for this, okay? One is if you get a positive change in kinetic energy, and the other one is if you get a negative change in kinetic energy, because this could go both ways. So the delta K could be an increase in kinetic energy, and the delta K could be a decrease in kinetic energy. And that would depend on if you have positive work or negative work being done. So if we have a positive delta K, a positive change in kinetic energy, this could mean either the object is speeding up, and that's one way to think about it, or the object is starting from rest. Let's just go ahead and just say or starting from rest. So it could have a zero kinetic energy at the very beginning, and that's worth noting. Starting from rest. So I'm going to write here in parentheses zero kinetic energy. So KE for kinetic energy, 0 joules of kinetic energy. That's one way to that's one way to think about it. So if you were writing this out as an equation, if the object is starting from rest, the Kf minus Ki, the Ki would just end up being 0. Okay, so your final kinetic energy would be the work that is done. So whatever the speed of the object is after it began from rest would be the work that was done on the object itself. Okay, the network being done on the object. It takes into account the fact that you will probably lose some energy due to friction as well too. So if you add up all the works together, it will do that. The other situation is if you have a negative delta K. And if you have a negative delta K, that means that you're losing kinetic energy. The only way, yeah, the only way that you're losing kinetic energy is if you are slowing down or if you are stopping. Okay? So we can either say that the object is slowing down or the object is stopping. So object is slowing down or the object is stopping. Okay, it's also important to note, I'll go ahead and I'll write this out. Since we're saying the object is stopping, object being stopped is 0 kinetic energy, but it's going to be backwards this time. So kf minus ki, the ki is going to be a number and the kf is going to end up being 0. So this number is inherently negative, which means that whenever you have a negative delta k, this is normally going to imply negative work being done on the object. Okay? Negative work just means instead of storing that or instead of actually using that energy to um, move an object from one location to another, you're spending that you're spending that energy and it's going somewhere else. It's leaving the object, okay, or it's leaving the system, for lack of a better word of what I'm trying to say. So if an object is speeding up, then energy is coming into that object. If an object is slowing down, energy is going away from that object. You're spending that energy somewhere, some way, shape, form, or how. Okay. Let's see here. There's another important part about this, and I need to kind of think about it to find out what it is. Um, you can change kinetic energy into work. In fact, the change in kinetic energy is work. Okay, so like that is thing. You cannot change one kinetic energy by itself into work. Does that make sense? So like if you have an object, yeah, so like if you've got an object that's going down the road and the object is going like 60 meters per second, if you don't have any other information about the speed of this object, then there's no change in kinetic energy. So the delta K, if it's moving at a constant speed, is equal to 0. Okay, so there is no net work being done if something's moving at a constant speed. Okay, I shouldn't say no. I should say there is 0 net work being done when an object is moving at a constant speed. Okay, see, I said no, and I needed to really say 0 network because obviously the object is moving. If it's moving at a constant speed on Earth, the engines have to be pushing it forward, and friction has to be pulling it backwards. So there are forces, there is work being done, it just cancels out. The network is 0. Okay, so in this case, our change in kinetic energy is 0, which implies to us that our network is 0, which implies to us that no work is being, or sorry, I did it again. 0 work is being done. Okay, 0 work is being done. All right, does that kind of make sense? Are we all okay with that? It doesn't hurt us too terribly badly? This is just another way to think about this. And usually interpreting it in terms of energy is an easier way to do things than measuring force times distance. And I will show you the reason why. Okay, so I'll go for this. Like, why use the work energy theorem? And the answer is it's handy. It's very handy to be able to do. Let's say that we have an object and we were going to. Y'all want to use a car example or you want to use an inclined plane example? We haven't done an inclined plane in a long time. Oh no. Oh no. Why do you do this to us? Um, let's just say that an object is sliding down an inclined plane because we haven't done an inclined plane in a while. That's been from like dynamics. Oh crap, we did do one yesterday, didn't we? Okay, but hang on. So like, let's just say that our object has a mass of 5 kilograms. Okay, and we want to try to find out like how much work is going to be done by this object. We have a couple of different ways that we could figure out how to do this. Okay, the first way that we could try to find out was what we figured out yesterday. So from yesterday, what we could do is here was our workflow. We draw out the forces, and then we calculate the work. Okay. And what else did we do? I'll go ahead and I'll draw the pictures. There was a force going down this way. What other forces did we have acting on this box? That wasn't just one. There's definitely a normal force, right? Okay. And there's one more force acting on this. Let's say that this object is sliding down the ramp. There's definitely friction. What direction is friction pointing? The opposite direction of motion. So we're going to put friction going this direction, the opposite direction of the motion. Okay, so we drew out our forces. We know that there are 3 individual forces here. Yesterday they were 4 because somebody was pushing this up a ramp. If we were just sliding down the ramp, there's just going to be 3 different forces acting on it. And we calculated the work done by each force. And then after we calculated the work done by each force, what did we do? We did. Yeah, we added them all together, right? So we summed them together. So we add together to find the total work. Okay. And when we did that, I think that gave us the network of the object, right? The work energy theorem will give you another way to actually do this, because if you can find the velocity of the object, then you can find the net work. This thing started from 0. It started from rest, which means if you can find the kinetic energy once it reaches the bottom, you have the change in kinetic energy. So instead of actually having to take all of our forces and add them together, we could end up using the kinematic equations. So this is, I don't know, what do you want to call this? This is like um, this is not the work energy theorem. So this is just using net work and just adding them all together. So if you want to use the work energy theorem, what we would use is we would kind of work through the kinematic equations, which we already know how to do. So what we can say is we can say, all right, well, if I can find the velocity of this object down at the bottom, then I can use that velocity to find the work being done, because I know that the net work on the object is equal to the change in kinetic energy. Okay, in this case, since that's the final kinetic energy minus the initial kinetic energy, the initial kinetic energy just ends up being 0. So the net work that got done on this object is just equal to the final kinetic energy, which is 1/2 the mass times the velocity of the object squared. And the good thing about this one is if we can find this velocity, we have the answer. Okay, that's it. Because we've already got the mass, we know that that's 5 kilograms. So if we can find that velocity, we are good to go. We just have to find it. That's the hard part. Okay. And in order to do that, we would have to use the kinematic equations to be able to solve for that. Yeah. It is going down the ramp. Okay. This object is moving down the ramp. Does it look like this object is moving up the ramp from the force diagram? Kind of does, doesn't it? Okay. Should I redraw my forces? Maybe if I make the friction not as large, maybe it would look like it's going down the ramp. How about this? If I give it like a baby arrow, is that okay? Okay. Gravity, I would not have an arrow opposite of the friction because that arrow opposite of the friction is right here. Okay. This arrow that is opposite of the friction is this one down here. Okay, so we have a force of friction that is we have a force that's going down the ramp, and that force going down the ramp is greater than the force of friction, or else it would not move. And that force that is going in the direction of motion down the ramp is the horizontal component of the 5 kilogram mass. Okay, which means we'll have to do a little bit of our sine, cosine, and tangent in order to be able to find that out. Okay, it does. Yeah, like I do have an ink to shape button, and I totally just like don't. Yeah, you're right. It's true. It it makes it look more distinctive. That's my story, and I'm sticking to it. All right, let's go. Let's go for this. Let's see here. We need to find the acceleration going down the ramp, which means because In order to find the velocity, we have our choices. We can either do vf squared minus, let's see, oops, equals, vf squared equals vi squared plus 2ad. Y'all better double check me and make sure that these equations are right. Vf equals vi plus at, and displacement equals vit plus 1/2 at squared. Okay, I think these are correct, but y'all do need to double check me. We haven't. The forbidden equation. What was the forbidden equation? D equals vi plus vf, all divided by 2 times time. Okay, so here's the deal. If we're making this thing go down the ramp, time is probably the least likely thing that we're going to have. Yeah, so if we're going to do a problem with the work energy theorem, my bet is that it's usually going to be with this vf squared equals vi squared plus 2ad, because we usually don't have the time that it would take to actually do that object. Now, does that mean that they might throw a problem at you guys that where it has the time? Sure, they can totally do that. Any kinematic equation that we have used in the past, we can now use to find the work done by the object using the work energy theorem that connects energy and work together. Do what? There are as many kinematic equations as you want to solve for. So there are some more kinematic equations. They become less useful though. So like for example, technically you could solve each one of these equations for t, and it would make its own kinematic equation. And then some people would argue that, well, wait a minute, you're really just solving the same kinematic equation. It's the same thing, just solved for a different variable. But I'm going to go ahead and break this to you. All of these equations are based from the same thing. So there are lots of kinematic equations. These are just the ones that usually end up covering all the bases. So with a little bit of algebra, we could rearrange these and do them any particular way that we wanted to. But all of this stuff comes down from the acceleration is equal to delta v over delta t. And they just take some different parameters for acceleration and velocity and put them in there. Now, that's what we're going to assume. Now, ideally, what'll happen is it'll slide some distance past the ramp. And we'll do some problems where it will slide down the ramp, hit, and then we'll determine how far it slides using the coefficient of friction. It'll just like flip over. It'll just stop. Just deadpan right on the bottom. Fair. All right, so if we're going to do vf squared equals vi squared plus 2ad, we're going to need the distance that it traveled down the ramp, and we're going to need the acceleration. So we'll need some pieces of information. First of all, let's say that this is a 10-degree ramp. Second of all, let's say that we were going down the ramp and that the total distance was 5 meters. Third, we're going to need, actually that might be it, because we can find the acceleration from the 5 and the, yeah, I think we're good. Okay, here we go. Third, acceleration due to gravity is negative 9.8 meters per second squared. Good. Yeah, we already know that piece of information, but we're going to need it to be able to solve this problem. Okay. Let's go. How would we find the acceleration of this object going down the ramp? Oh, third. Okay. I got a real third for you. I was sounding real confident at the very beginning. Third, the coefficient of friction here is 0.10. We will need the coefficient of friction because there is friction involved. Okay. What were you saying? We are going to need the sine of theta. So let's write out our forces. In the direction of motion, the direction of motion is down the ramp. So what forces do we have down the ramp? The sum of the forces in the x direction, x being down the ramp. Okay, so force friction plus, well, not gravity, but the it's related to gravity, right? It's like a part of gravity. So Fg sine theta. Yeah, because it's going to be the opposite side. Because remember, this 10 degrees is the same thing as this 10 degrees up here. So this opposite side is going to be mg sine theta. and this side up here is going to be mg cosine theta. So the opposite side to the normal force is going to be mg cosine theta. The opposite side, or no, the opposite to friction is going to be mg sine theta. Okay? Now, the force of friction, we can actually expand this out. This is, we can't just write F of F. That doesn't really help us. Friction is fun. Yeah, friction is fun. So F mu n. Okay? And plus, we know that the force of gravity is mg, so that's mg sine theta. One of these is negative, though. Which one do we want to make negative? This is going to be equal times. Okay. So even though gravity is pointing downwards, we're going to make friction negative. I see how it is. It's okay. It doesn't matter. Right. Okay. So downward is negative and upwards is positive. We're going to go with that then, huh? Okay. So then since this is friction, this is going to be this is you're right. It's going to be the negative direction. I'm going with it. I'm going with it. So we know the coefficient of friction is 0.1. We know that the normal force is mg cosine theta. So that's going to be, I'm going to write this out to the side. It's 50 newtons for mg times the cosine of 10 degrees, which is something. I don't know. I did not do very good on my angles. That's going to have to be a calculator question there. 50 times the cosine of 10 is a number, and we can't go any further until we get that number. I'll need a number in a second. Do our little chance to calculate. 49.24. Okay, do I get a second? Yes, 49 point, let's go 2, 49.2. And then mg sine theta is going to be 50 times the sine of 10, which is going to slow us down again. So 50 times the sine of 10 gives us a number. And then we're going to have to crunch all these numbers together. 8.6. Okay. So we've got 8.6 and 4.96. Oh yeah, it's negative 4.92. That's true. Let me put that in red so that I don't. There we go. Red, negative. Red, negative. And then add those together, and that gives us the net force acting on the object. And that's equal to the mass of the system times acceleration. 3 what? 3 point. Do not say 3.14. Do not say 3.14. 3 point what? There's no way. There's no way I could have done that on purpose. Okay, good. Yeah, 3.68. Yeah, 3.68. Some Broadway just gets like super genius mode and like just metas this thing. Be like, oh, hey, look, we got pi. Yeah, not intentional. 3.68. What? What's the unit for force? No, no. Newtons, not joules. Joules is energy. Newtons is force. Okay, 3.68 newtons for force. They are not the same thing. Joules is force times distance. Joules is force times distance. Newtons is mass times acceleration. And you multiply it by a distance, you get it. Yeah, no, it's I'm done. All right, 3.68 newtons. Now we know that the mass of the system is 5 kilograms. So all we have to do now is just divide this 3.68 by 5, and we have our acceleration. The kilograms are going to cancel out, and you'll be left with a meter per second squared. How much is it? 0.736? What? Okay, 0.736. 0.736. Let's go 0.74 meters per second squared. You really want me to do 0.736? Ugh. Ugh. Somewhere in the YouTube universe, there's a physics teacher just screaming at me for my lack of decimals in this, but lack of significant figures will be okay. I can take the heat. We'll be fine. Do what? Do what? Right, yeah, it's like I'm like, "Hey, let's round this." And you're like, "No, let's not." Be like, "Why not?" Sig Figs are your friend, but I'm not the AP Chem teacher, so whatever. All right, so your acceleration is 0.736. Now, since you found this acceleration, we can use this to find the velocity. So VF squared equals VI squared is 0 plus 2 times 0.736. Now, was that a positive or was that a negative? Okay. 0.736 times D, which is 5. Okay. And then, so the velocity squared is 7.36 meters per second squared, meters squared per second squared. Okay. Right. So we need to take the square root of both sides, right? So if you do this times this, you get a number. 2.71 meters per second at the bottom of the ramp. Okay? True story? All right. That's fair. That's fair. Um, and this makes sense because we made right positive, so that 8.6 for gravity is a positive number. So since we got a positive meters per second, that doesn't hurt my feelings. It's a little weird, but we'll be okay. So since we've got that velocity, we can now find the work being done on the object. So the net work is going to be equal to the change in kinetic energy. So that's just going to be since it started with 0, that's going to be, kf minus ki, but the ki is 0. So the kf is just 1/2, 5 kilograms times 2.71 squared, and that'll give us how much work was actually done going down this ramp, which is a number. In joules, yeah, it is a number that we should find. Half of 5 is 2.5. 2.5 times 2.71 squared is, I don't know. I really wish I had my calculator. When we have calculator times, 18.3. Do I get a second? Okay, 18.3 what? Okay, 18.4 joules. Listen, look, come on. Come on. No. 1, 2, 3. No, 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 no. Sig Figs. You don't understand Sig Figs. 1, 2, 3. 1, 2, 3. So, yeah, the 0.736 would have 3 Sig Figs, yeah. 1, 2, 3. Okay, so it looks like throughout this entire problem, we've been trying to strive to keep 3 Sig Figs in our calculations. That's my hope anyway. Okay, now, I don't really, in AP Physics, we don't have to worry about sig figs. They just say like don't cut off things to like the nearest whole number and don't go super crazy on decimals. Like it's unnecessary. Like if you can just give us like 3 or 4 significant figures or 3 or 4 digits of precision, you're normally just fine. So if you normally round it to the nearest tens place or hundreds place, you're normally good to go. They don't spend a whole lot of time and effort on the significant figure part of the calculations. If you want to get traumatized on that, AP Chemistry is the class that you want to take for trauma on that. Okay. All right. I don't think anybody in here is in AP Chem. Let's see here. I don't think anybody in here is in AP Chem. We have 18 minutes left. So, do y'all want to do another? Do y'all want to do a practice problem? What do you want to do? Demon hybrid baby? What's the what? Something with wheels? What? Do what? How we would solve it with wheels? The same exact thing. Okay, no, okay, that's fair. If you take the exact same problem that we just did, where you've got an object sliding down the ramp at 5 kilograms, just sliding down the ramp, and you put wheels on it, that will lower the friction between the ramp and the object, which means your acceleration will increase, which means that you will actually have a larger acceleration, okay? Your final velocity will be the same, but since you had a larger acceleration, um, it honestly won't make a difference at all in the amount of work being done. Okay? Because of even though the acceleration changes, when we calculate the acceleration and we look down here, vf squared equals vi squared plus 2ad. Let's see here. I might have lied to you. Oh, here's the problem. I think I know what the problem is. When we calculated this, we calculated the net work done, right? So since there's less friction to take it away because you put wheels on it, then the work will actually increase. The net work will get higher because you had less work from friction taking it away. In a normal system where there's no friction involved, the amount of work done would be independent of the acceleration. Okay, so like it really wouldn't matter because you're just if you're storing work up or if you're getting rid of work in a conservative force, like a gravitational field or something like that, it doesn't matter the acceleration. Okay, the thing is that you're doing work. However, since we don't have that situation, and since there is friction involved, since you put wheels on it, you are decreasing the friction, and therefore you are increasing the amount of useful work being done on the object. Okay, so how would that change our scenario here? Our network would increase because our acceleration would increase, and therefore it would also, because of the lack of friction, I guess it would also increase our velocity. Since it increased our velocity at the end, that means we have more kinetic energy. Since we have more kinetic energy at the end, that means we've done more net work. That's fair. Any other questions? Okay. Um, let's see here. How about our good friend the Atwood machine? We haven't done one of those in a while. Yeah, remember what the Atwood machine does? Yeah, is the pulley is the yeah, it's kind of like a scale, yeah. And on one side, let's say that on one side we have a mass of 2 kilograms. Are you kind of starting to see how these are going to start rapidly becoming demon hybrid baby problems? Because they just take our concepts that we've learned before and it just like talks about it in a different way. Say that this one's 4 kilograms. Obviously, the 4 kilogram one is going to pull the 2 kilogram one. Now, which way do y'all want to make up and which one do y'all want to make down? Which one? Which one we want to make up or down? Well, Which way is down negative? Because remember, this is going to go this way, and this is going to go this way. The 4 kilograms going down is negative. Okay, so we're going to make this is negative, this is positive. That means on the other side, this direction going up is negative, and the direction going down would be positive. Okay, so let's just say that during the time of the Atwood machine going from one location to another location, let's say that it travels over 1.5 meters of distance. So it's just going down. And what we would want to try to find out is how much work was being done. Okay, how much work was done by the 4 kilogram mass. Just the 4 kilogram mass. Specifically the 4 kilogram mass. Only the 4 kilogram mass. How much work was done? What would we do? Okay, after we cry, what would we do? After you cry some more. Okay, so we could do that. We could do that the network is equal to the change in kinetic energy, right? That would be the network. Now we're only really interested in the 4 kilogram block. We're not really interested in the 2 kilogram block. So when we calculate mass, we'll just be using 4. Okay. However, this thing is going to accelerate and it's going to move down, and it is going to be tied to that 2 kilogram mass. Okay. So if we're going to do it this way, we're going to have to find the acceleration because this is going to be kf minus ki. The final kinetic energy is a number. The initial kinetic energy, let's just say that it started from rest. Okay? Now what? Yeah. So this thing is moving down. It's moving down 1.5 meters. Okay. What are its forces? Okay, so we should probably draw a diagram, right? All right, so we have 40 newtons going down this direction, right? We have a tension that's pulling up that we'll call T. We have a tension over here that should be identical to the tension on the other side. And we also have a force of gravity pulling up this way. I pointed down, but it's positive, right? We have a force of gravity pulling up at 20 newtons. So this would be negative 40 newtons, and this would be positive 20 newtons. Okay? So if we calculate the sum of our forces going in the direction of motion, what do we get? If we get the sum of our forces going in the direction of motion, what do we get? Okay? It's not, okay, it's got to be positive 20 newtons. So positive 20 newtons minus the tension plus the tension. Hey, listen, we described what we wanted to make positive and negative, and you were paying zero attention at the time. So if you're not paying attention at the time, you don't get to pick. You do not get to pick. Minus 40 newtons. We have decided that gravity going down is negative. So sorry. And all of that is going to be equal to the mass of the system times the acceleration. Okay. Newton's tension cancels out. So bye-bye, bye-bye. And then the total net force acting on this would be 20 minus 40. So that'd be negative 20 newtons is equal to the mass of the system. That would be 4 plus 2, which is 6 kilograms. And that was times the acceleration. Okay, so that means that the acceleration is going to be equal to negative 20 newtons divided by 6 kilograms, which is a something. Negative something. 6, 12, 18, negative 3 and a third. Say negative 3.33 meters per second squared. Okay, that's fair. That's fair. Since we found the acceleration, we can now find the velocity of the object, so we can find the kinetic energy of the 4 kilogram block. Okay, so of the kinematic equations, there's really only one to kind of pick from because we just don't have time in these problems. Okay, so if we don't have time in these problems, then we're going to use what? Okay, we've got to pick out VF squared equals VI squared plus 2AD. We want to find the velocity. We know that the initial velocity is 0. That goes away. So it's going to be VF squared equals 2 times negative 3.33 times the distance, which is 1.5 meters. And so that means our VF is going to be equal to the square root of all the, oh no. There we go, yeah. So since we're going down, that's going to be negative 1.5 meters. So our negative square root ends up not blowing up things. So it's 3.33 times 1.5. I'm going to just go ahead and a negative times a negative is a positive. 1.5 meters. There we go.
3.16.
With the square root?
Yep, not squared.
Okay, so VF is equal to
3.16.
3.16 meters per second. Is everybody okay with that? Do I get a second? Okay. So our final velocity is equal to 3.16 meters per second. We can now find the work being done on the object by using the net work, finding the kinetic energy. So the net work is going to be equal to 1/2 the mass of just the 4 kilogram block times 3.16 meters per second squared. So that's half of 4, which is 2. 2 times 3.16 is, oh, sorry. It's 2 times 3.16 squared. I was going to do 2 times 3.16, and then I realized that my calculating abilities
19.97.
quickly diminished. 19.97. 19. 19. If we're going with 3 Sig Figs, and it's 19.97, what do we do?
19.9.
No, that would be rounding down.
Wait, 20.0.
If you calculate it and it says 19.97 and it's meters per second and you're trying to go 1, 2, 3, we have to round this up to 20.0
Okay.
meters per second. So it'd be 20. Oh, I'm sorry. I'm dumb. It's not meters per second. It's energy. So energy is measured in joules. So it'd be 19.97 joules, or if we try to round it to 3 sig figs, 20 joules, 20.0 joules.
So
Okay.
technically, you're still wrong.
Newtons and joules are always easy to get confused with each other because kilogram meters per second and joules is kilogram meters squared per second squared. They're really only off by a distance, so it's really easy to get joules and newtons mixed up with each other. We even use them in force problems. Once you calculate the force times distance equals that. And it gives you 20 joules. Okay? Now there are some other ways to do this as well too. And we'll kind of go over some other ways to do this. So as we keep learning about like work and how this functions, or the work energy theorem and changing using kinetic energy, we're going to figure out there's some other ways to do this kind of stuff as well too. And as we continue moving along, hopefully we'll find the ones that work the easiest out for us whenever we get there. Okay. So later on, if you find out that there's an easy way to do this, then that'll be okay, and then we just learned in the process. But I'm gonna go ahead and stop the recording because we've got what 3 minutes left. So 6 minutes. We can't do a problem in 6 minutes. So I'll take it easy on the virtual kids.